One thing about this using all the training instances is commonly we have many more than 6 training instances. We might have tens of thousands, hundreds of thousands, millions, in Google scale, billions, OpenAI scale. So we might not want to deal with all of them. One advantage of dealing with all of them is we have a very deterministic process. Okay? This step of calculating the loss, calculating our y-hats is deterministic. Calculating the loss is deterministic for a given training instance, and the overall loss is deterministic. And then our optimizer lets us move and so on. There is something called stochastic gradient descent. So stochastic gradient descent says update theta based on one training instance. So in the traditional gradient descent, we again are using the entirety, the loss for every single training instance, and using that to figure out what the gradient is, and then updating theta appropriately. Here, what we're saying is, let's actually look at the loss for a given training instance. So the idea is actually, we will just take all these training instances and grab one of them randomly. Randomly is why we get the word stochastic here, right? So at random. So let's say we do this one. This one, we will go ahead and calculate the gradient for it. So in fact, for this one, we know what the gradient is, right? The gradient is negative 4.8 and 14.4. So instead of using negative 2.9 and negative 5.8, we're going to use negative 4.8 and negative 14.4. So that will then update B and M, in fact, larger than they are in the overall loss, which makes sense because this guy has a greater than average loss than these two. And then go ahead and update theta. And then go ahead and pick another training instance and do the same thing. And another training instance, do the same thing until we've gotten through all of them. Now, one thing to note, if we hit this training instance is actually going to say, we don't want to increase B, we want to decrease B. We don't want to increase M, we want to decrease M. So sometimes we're going to be going in the wrong direction compared to the overall direction, looking at the entire loss, would tell us to go through. But that's okay. That stochasticity is one way, in fact, that we can avoid or get out of local minimum. Right? We can have a training instance that says, instead of moving M by 5.8, let's move it by 14.4. So instead of moving a little bit here, maybe we're going to move enough to get outside of this local minimum. Or maybe we'll go in another direction, like left instead of right, and that may get us out of that as we look at this entire multidimensional picture. So we have this possibility of either one training instance or n training instance. So this is stochastic. Let's see if I not write it. Let's just call it SGD. And this is the entire data set. We can also do something in between. Oh, first off, an epoch is still a training loop through all the training instances. In this case, a training loop through all the training instances means we do one training loop and we've gotten all the instances. In this case, if we have n instances, we have to go through this n times. Okay, n training loops. Okay, and that'll get us through all the instances, and that's one epoch. So one epoch is basically touching or looking at all of the training instances and adjusting theta based on it. And what's the advantage of this? This takes a lot of computation. If we look especially at the very beginning when we have our random theta, there's a lot of computation here to go through to look at all of the training instances to figure out, do we want to increase or decrease the various components of theta. Instead, it might be simpler to just look at one training instance, and that'll get us a little closer because our theta is way off. And so by looking at almost any of these training instances, it'll be taking M and B in the right direction. And once we've taken it in the right direction, then we have a better y-hat. So as soon as we've gone through this loop once, our y-hat should be better next time. And again, it'll be better and better and better. So after one epoch of stochastic gradient descent, we've probably got a much better value of theta than after one epoch of just looking at the loss across the entire data set. So one update of theta is probably less good than having all n updates of theta, okay, because we started going in the right direction. And as we're halfway through, we've made some progress in theta, so we're getting better values. There's also an in-between. So the in-between is batches. So the idea is, let's say we had a batch size of 2. That would say, take this data set, randomize the order, and pick then the first 2 from that random order. Go through the loop. Then pick the next 2, go through the loop. The next 2, go through the loop. So when we're calculating our average is not the average across the entire data set, it's the average across the batch. So we will calculate 2 y-hats and calculate the average across those 2 loss. Update theta, next 2, next 2, next 2. Okay, so these are often batches of size k. So this is our intermediate between 1 and n. We still have stochasticity, but it's more regular, right? There's less wild fluctuations because so for instance, if we look at this one where one instance has 2 positives, here this is never going to be by itself. It's always going to be averaged with some other. So we have kind of the best of both worlds. Guess what k is? The decision of what your batch size is, like deciding it's 2. This is a yap. A yap is yet another hyperparameter. Y-A-H-P. There are lots of hyperparameters that you need to choose. When you look at the literature, when someone is describing in a particular paper their results, they will always, or should, so that we have reproducibility, always specify what their choices of hyperparameters were. They used the batch of this size. They used a learning rate of this. The optimizer they used was this. This was the loss they were using. This was the function they were using, and so on.